we begin with our canonical foam chunk on the XY plane. We specify a point X0, Y0. And the first thing we look at is what happens if we lay this thing over on its side. If we move in the X direction, then we're moving along a line right here. And if we turn this over on its side, we can see the triangle formed by the edge and by the horizontal or the flat horizontal direction. That direction could be described as the intersection of a plane parallel to the XY plane at the point X0, Y0, f of X0, Y0. In any case, this x derivative we can estimate to be about 0.25. It looks like this is about a quarter as big as this, so that fx appears to be approximately 0.25. Now if we cut the thing with a plane parallel to the XY plane here and turn it over on its side, we can see that y displacement is this way, the change in the f function is this way, and we get a triangle that looks something like this with a slope of approximately 1. Now we're heading for questions related to the derivative in the direction of a unit vector u, but we're not there yet. Let's just take what we've already got. We see then that a unit tangent vector in the x direction, well, would be a vector who comes out in this that comes out in this direction and up in the y direction, and perhaps the unit length is equal to the length of this Sharpie, so the unit vector would have a slope essentially of 0.25. If we moved, well, I don't want to make this a unit vector. We go a unit vector in this direction, then a vector in the direction of this edge could be that unit vector, which would be the I vector, plus 0.25 times the k vector. So that's what we have here. We have I plus 0.25k, and of course that represents I plus the x derivative times k. Understood that the x derivative is evaluated at the point x0, y0. And similarly for the j direction, if we go a unit distance in this direction and then an equal distance in this direction, it appears that we would have a vector that's parallel to this edge. So that vector would be j plus 1k, or more generally we'd have j plus fy times k. If we take the cross product of these two vectors using the general form, we get a vector normal to this. Well, let's back up for a second. We have a plane that's parallel to the plane of this surface. Okay, this plane could be pictured as a flat piece of glass, a flat piece of or just a flat region. We understand how to visualize this tangent plane, and that tangent plane will have normal vector that's the cross product of any two vectors, any two non-parallel vectors within the plane. This vector is in the plane, this vector is in the plane. One vector along this edge, one vector along this edge. So when we take the cross product, we do get our normal vector. From the normal vector in the point x0, y0, we have the point on the surface. We have x0, y0, f of x0, y0. F of x0, y0 would be this distance, so the point x0, y0 would be here, and the point f of x0, y0 would be right at this corner of our foam chunk. The tangent plane, which can be obtained by methods we're not going to repeat here, we simply dot the normal vector, though, with a vector from the point x0, y0, f of x0, y0 to a general point x, y, x, y, z, and taking that dot product and acknowledging that the point x, y, z will be on the plane, provided that dot product is 0, we get the equation of the tangent plane. Now we consider unit vector u, and that unit vector will make some angle theta with the positive x direction, and we want to see what happens Well, okay, now I've got this knife here. We've got a plane parallel to the u vector and in the vertical direction, in the k direction. So this plane is perpendicular to the xy plane. We ask what would happen if we cut the surface parallel to that plane. Now let's see what the representation of that plane would be. The u vector, if it makes angle theta, is u equal cosine theta I plus sine theta j. So we want a vertical plane, a plane which is perpendicular to the xy plane and parallel to the u vector, that is, contains the u vector. Now, in order to get that plane, if it's parallel to the u vector, then it's normal to any vector that's perpendicular to the u vector. What's a vector perpendicular to the u vector? If we just reverse the x and y components and make one of them negative, we get a vector perpendicular to the u vector, so that this vector is going to be a normal vector to the plane that we're talking about, the plane with which we want to slice this piece of foam. If we know the angle theta and the coordinates of the point x naught, y naught, it's an easy task to find the equation that intersects, the equation of, let's go back. Okay, again, if we know x naught, y naught and the angle theta, it's easy to find a plane through x naught, y naught normal to, and I've got that written wrong, cosine theta plus cosine theta I plus sine theta j. I'm going to take a slip of paper here and write this correctly. This is negative sine theta I plus cosine theta j, and that would be the normal vector. Okay, we've taped that down. Probably not all that legible, but the normal vector is going to be the sine theta, negative sine theta I plus cosine theta j. So to review where we are, we've noted that we can find the equation of this plane, and we have an expression for the equation of the plane along this surface. If we intersect these two planes, intersect the tangent plane, which runs along the upper surface of the foam chunk, with this plane through x naught, y naught, normal to negative sine theta I plus cosine theta j, we get this blue line here along the surface. Now that blue line has some slope with respect to the xy plane. It's parallel to the u vector. It's in the plane, the vertical plane that's defined by the u vector and the point x naught, y naught. And there's some angle between here and here. Now, that angle, of course, I can move this u vector any place I want. If I move this u vector over to the base or the point of intersection of this line with the xy plane, then I can see that the angle is just the angle from the xy plane to here, and that's going to be the angle of this intersection line with the u vector. In that sense, we say that the intersection line has a slope with respect to the u vector. Again, if the intersection line is here, then this line has a slope with respect to its representation within this vertical plane. The intersection line, represented by this blue line, the u vector, direction of the u vector, represented by the red arrow. There's an angle here that I originally called theta. Changed that to phi because, of course, we've already used theta here. So we have the u vector, the intersection line, the angle between them. All that is going to be better represented in very tangible terms if I can actually slice this foam chunk along this plane. So I'm going to take it off camera. I'm going to do the gory deed off camera, and then I'll come back with the two pieces. And of course we'll pause the clip while we do that. Okay, the foam chunk has been split. Now let's go ahead and take it apart. Actually, I guess the blue line is more on this half than on this half, but let's just go ahead and shade in a blue line along here. And if I lay this flat, then I see that, of course, the XY plane would be in this direction. So if this foam chunk is sliced by a plane parallel to the XY plane at this point, at the point of our graph, our x0, y0, f of x0, y0 point, then we're going to get something that looks like this. When this is elevated, that line becomes parallel to the XY plane, angled out parallel to the u vector. And right here is my angle phi. And now the payoff statement, the slope of this intersection line with respect to the plane parallel to the XY plane is just our our directional derivative in the direction of u of the function f when that directional derivative is evaluated at the point x0, y0.